I realize I put my grid up here too soon, so just ignore that polar grid for just now. If I ask you to graph y equals x squared, it should end up looking something like this. Let's say you only use really wet ink on one half, but then you fold it down the center, say down the y-axis. That's where your fold is. When you unfold it, you'll have a perfect mirror image of the graph, which I am not going to be able to do. That's not too bad. And that's called even symmetry. We've met this before. Algebraically, we say that this is what happens when f of negative x is equal to the original function. It just means that if you plug in a positive 2, you're going to get a positive 4. But if you plug in a negative 2, you're still going to get a positive 4. Their output's going to be the same whether you plug in a negative 2 or a positive 2. You might also hear this called y-axis symmetry or vertical symmetry. It has a few different names. It turns out that y equals the cosine of theta is an even function. If you graph y equals the cosine of theta, and you plug in, say, a positive, let's see, that's pi, so let's pi over, well, let's not use that example. There's a pi over 4. There's pi over 4 right there. If you plug in positive pi over 4, you're going to get this value. That's a square root of 3 over 2. And if you plug in negative pi over 4, sorry, that's 1 over root 2. If you plug in negative pi over 2, pi over 4, you're still going to get positive 1 over square root 2, right? So no matter whether you plug in a positive or a negative pi over 4, you get the same positive value out. That's how we know cosine is an even function. We also have something called odd symmetry or odd functions. An example in algebra is y equals x cubed. That graph looks something like this. Okay, let's pick a point on this graph. This x value is a positive one, right? Because it's to the right of the y-axis. When I plug in that positive x value, I get, let's use actual numbers here. If this was 2 in the function y equals x cubed, then I'd get 8 out. But if I plug in a negative 2, I'm going to get a negative 8 out. So for this function, when I plug in a negative value, I'm going to get the same number back, but the answer will be negative. So this is what it means to be an odd function. And as it turns out, y equals the sine of theta is odd. And that's because the graph of sine looks something like this. Okay, and if I pick an odd, let's say, pick a positive. This is pi here, so pick pi over 2. If pi over 2 is positive, I get positive 1. But if I plug in a negative pi over 2, I get negative 1. So if you plug in a negative value and you get the same thing as you would have if you plugged in the positive value, then that's an even function. If you plug in a negative and you get the same thing as you would if you had plugged in the positive value, but it's a negative number, then that's an odd function. This is a kind of symmetry. This is a kind of symmetry too, but we're not going to talk about that one. It's just a little too complex, and it's more than we need for this section. But this symmetry is really easy to see. Like I said, if you folded this paper in half, you get a mirror image here. There's that kind of symmetry or similar kinds of symmetry in polar equations as well. So I'm going to erase the bottom half of the screen and use it to demonstrate something slightly different. I'm going to try replacing, oh, that should be an R, not a Y. I'm going to try replacing R and theta first with negative R comma negative theta, then with negative R comma positive theta, then with positive R but negative theta. I'm going to look and see what happens in each case. In the first case, I'm going to replace R with negative R and theta with negative theta. That gives me negative R equals 3 times. Now, the sine of negative theta is negative the sine of theta, because sine is an odd function. So that's going to be negative the sine of theta. If I multiply both sides by negative 1, I get R equals 3 sine theta. That's exactly the same as the original function. Here's my original function, and I got exactly the same thing when I made that particular replacement. Replacing with negative r positive theta, I get negative r equals 3 times the sine of theta. Multiplying both sides by -1, I get r equals negative 3 sine theta. That is not exactly the same as my original function. In the third case, I'm going to replace r with positive r, 3 times the sine of negative theta. That gives me r equals 3 times the sine of negative theta is equal to negative the sine of theta. And again, it doesn't pass this test. Do you remember what the graph of 3 times r equals 3 times the sine of theta looked like? It looked something like this. I'm going to try that again. Something like that. It was a circle, but instead of being centered at the origin, it was centered at y equals 1.5. There was no horizontal shift, right? If you look at the test that it passes and you look at the graph, the thing that we're noticing here is that we have what's called vertical symmetry, or in algebra we could call y-axis symmetry, but here we just have to call it symmetry with respect to the line y equals pi over 2. So symmetry, I'm going to abbreviate with respect to, you'll often see abbreviations like that in mathematical text, with respect to y equals pi over 2. And that, let me use yellow, that is what, wrong tool, how about a highlighter? That is what this test checks for. This test checks to see if you have some symmetry like, I'm going to kind of make something up here because we haven't really talked about these yet. Something like this, where there's a symmetry across this line here. You know how the point down here is called the origin if we're talking about Cartesian coordinates, but it's called the pole if we're talking about polar coordinates? Well, you know how sometimes we talk about the line y equals x as the origin as well? Oh, you didn't know that? Well, sometimes we do. So this line, I'm going to use this tool, also is called the origin. And so this test is called the test for symmetry with respect to the origin. But what we're talking about is that green line. Symmetry with respect to the origin. Algebraically, that's the line y equals x. This last test checks for symmetry with respect to the polar axis. And I hope you remember, but just in case you don't, that's equivalent to the x-axis in algebraic Cartesian graph, right? This line right here is called the polar axis. So we did a couple of examples in the previous screen. The first one was this one, and we tested that one already. We placed r and theta with negative r and negative theta. We got exactly the same thing back, and that means that this graph is going to have symmetry with respect to this line, right? So it's going to be equal on both sides of that line. Let's try another one and just see how it turns out. I got ahead of myself putting that up there. All right, I'm going to do these 3 tests. I'm going to check by replacing r and theta. I keep writing y equals here. That should be an r. I'm going to replace both r and theta with their negative cousins. Then I'm going to replace only r with its negative cousin and then only theta. So we'll start with the replacing both. Negative r equals 3 minus 3 cosine of negative theta. Negative r equals 3 minus 3 times cosine of negative theta is just cosine of theta. Multiplying through by, I don't even need to multiply through by -1. You can see that the right-hand side here is exactly the same, but the left-hand side is not. So this does not pass the first test. The second test is to replace just negative r and leave the theta positive. Well, theta is an even function, so what we're going to get there is Negative r equals 3 minus 3 cosine theta. Guess what? It's not the same. Pretty easy to see that, right? All right, so it doesn't have those two kinds of symmetries. Does it have the third kind? Here I'm going to replace theta with its negative cousin, but not r. So I'll have r equals 3 minus 3 times cosine of negative theta. R equals 3 minus 3 times cosine is even, so this is going to be cosine of theta. And that is exactly the same as the original function. So it does check, it does pass this test. So the graph of this thing, the graph of this function here, is going to have symmetry with respect to the polar axis. In other words, it's going to have whatever it does up here, it's going to do exactly the same thing in a mirror image down here. This is a subsection I don't normally teach, and I decided to throw it in there, primarily because in this textbook, it's the first thing in this section. So I wanted to address it, but I don't want you to worry too much about it. It is something that might help you graphing if you're graphing something by hand, if you're told you're not allowed to use a calculator or whatever. But by and large, there are a lot of great graphing calculator tools out there now. I am going to ask you to do a few graphs by hand, but by the time we get to the very end of the course, you're going to have some familiarity with what these graphs look like anyway, and so we're not going to linger on that. Graphing calculators are pretty powerful now. Now, if I told you how to do long division by just showing you in 4th grade which buttons to push on a calculator, you wouldn't understand division, and there's no way you could then go on to be the kind of person who programs calculators, right? So whilst I don't expect you to become an expert on these concepts, I do want you to have some exposure to them so that you can make the decision for yourself, so that you can understand the underlying ideas behind what's going on here. Once you know this, and once you've actually worked with it, rather than just pushing buttons on a calculator, you'll actually be able to make an informed decision about how you might want to use the information. You could, for example, go on to be somebody to design graphing calculators or logos, but that's a topic for the next section. For right now, we're going to be finished. I'm going to call this good for this video, and we're going to go on to the next subsection, which is graphing polar equations by plotting points.